Imagine you are listening to a complex musical chord. Your ear naturally decomposes that sound into individual notes, the fundamental and the overtones. In mathematics, Joseph Fourier suggested something radical, that any periodic function, even a jagged square wave, is just a combination of pure notes, sines, and cosines. Fourier began with the Fourier sine series. If a function is periodic, odd, and vanishes at 0 and pi, it can be written as a sum of sines. But how do we find the specific volume, the coefficients of each note? The secret lies in orthogonality. Think of sines like the x, y, and z axes in 3D space. They are at 90 degrees to each other. In function space, we check the angle between two functions by multiplying them and integrating. The math reveals a beautiful property. The integral from 0 to pi of sine nx times sine kx is 0, as long as n and k are different. Every term disappears except for the one where they match. Using this orthogonality property, we can isolate any coefficient, b. K, it is simply 2 over pi times the integral of our function times the sine of kx. Let's test this with a square wave. This function jumps from -1 to 1. It is a torture test for Fourier because of its sharp discontinuity. For the square wave, the coefficients turn out to be 4 over pi k for odd values of k and 0 for even values. This gives us a specific series of notes. Notice the 1 over k in the coefficients. This is the decay rate. It tells us how much high-frequency energy we need. A jump in the function leads to a slow 1 over k decay. When we use a finite number of sines to build this square wave, we see a peculiar wiggle at the jump, the Gibbs phenomenon. No matter how many terms you add, that overshoot stays at about 18% of the jump height. Despite the wiggles, these coefficients are the mathematically best choice. They minimize the total energy of the error. This is known as the least squares approximation. What if the function is even, meaning it's a mirror image across the y-axis? In that case, we use cosines. The first term, a 0, is simply the average value of the function. Cosines follow the same rules of orthogonality. They are the even notes of our mathematical orchestra. By combining sines and cosines, we can describe almost any function. The smoothness of a function predicts how fast its coefficients drop to 0. Think of it as a hierarchy of decay. First, delta functions or sharp spikes. These have no decay at all. High frequencies stay loud forever. This is the mathematical version of white noise. Next, step functions or jumps. As we saw, they decay at a rate of 1 over k, but if we integrate a step function, we get a ramp function. Because it has corners but no jumps, it decays much faster, at 1 over k squared. Finally, analytic functions like sines themselves are super smooth. Their coefficients drop off exponentially. The smoother the function, the fewer high notes you need to reconstruct it perfectly. There is a deep conservation law here called Parsevals' identity. It states that the total energy in the function equals the total energy in its coefficients. Think of it like white light. The total brightness of the beam is exactly the sum of the brightness of every color in its spectrum. While sines and cosines are intuitive, engineers prefer the complex form. Using Euler's formula, we can collapse the two formulas into one elegant summation using complex exponentials. This isn't just for waves on a string. Fourier series help us solve Laplace's equation. If we know the temperature on the edge of a circle, each Fourier note tells us how that temperature flows into the center. Consider the heat equation. The change in temperature over time depends on the curviness of the temperature in space. High-frequency notes have more curviness, so they dissipate much faster than the low notes. Let's apply this to a few problems. First, the function sine cubed of x instead of integrating, we can use a trig identity to see that it is actually already a Fourier series with two notes, 3/4 sine x and -1/4 sine 3x. Next, the absolute value of sine x, because this is an even function, we use cosines. The result is a series where only even harmonics exist, starting with the average value of 2 over pi. Finally, the function f of x equals x. This is an odd function, so we expect a sine series. Using integration by parts, we find that the notes oscillate in sign, creating the sawtooth pattern that builds a simple linear ramp. Joseph Fourier's insight changed mathematics forever. By viewing functions as a collection of notes, we can solve heat flow, analyze signals, and even understand the structure of the universe itself. Thanks for watching. If you found this explanation helpful, please like and subscribe for more mathematical journeys. If you enjoyed this deep dive into the music of functions, hit the like button and subscribe to stay tuned for more visuals on the beauty of mathematics.